Okay, hi guys. We have 6 people. It's a little bit lower than normal, but we can get started. Okay, so in the last class we talked about the state that is not the eigenstate, right? It's a superposition of the ground state and then the first excited state in the potential well, infinite potential well. And then one thing we found out, right, by calculating the expected position of the electron is that you see that it's actually moving inside the potential well. And this is actually something coming from the quantum interference, because if you look at each of these individual eigenstate, their expected position is always at the center. But then when you add 2 of them together, and then because they have a time term, and then because this is a wave, then they will have interference, and then you get a cosine omega t, 3 omega t term which moves your particle from left to right, right to left, and then doing this periodic oscillation like in a harmonic oscillator. Okay, and then so takeaway from the previous class is that in quantum, interference is always a very important thing. And after calculating the expected position, one thing you can see is that the expected position is time dependent. That means there's a velocity of your electron. So that tells us that there should be, if we calculate the expected momentum here, so 1, 2 here indicate that it's this state, it's a superposition state between ground state and excited state. So if we calculate this momentum, okay, if the meaning of momentum in quantum mechanics is the same as the meaning of it in classical mechanics, which means something is moving, then you have momentum, then we can expect that this momentum expected value will not be 0 and will also be time dependent, right? And one thing we've already briefly discussed last time is that how do you get the momentum? And then we already introduced a wrong approach, which is the approach is that you take sine x as e to the ix minus e to the minus ix divided by 2I. Right, and if you do that, and then then to this, can one of you turn on the camera? It's suddenly become a little bit weird. I'm talking to empty room. Thank you. Yeah. So what you can do here is that you can make sine into exponential ix, which will actually in a free space will represent the momentum eigenstate. So if we can write it down like this, okay. Okay, and then the first one is e to the minus I omega naught t, and then this is sine become e to the I pi x L. Okay, that's the first term, minus e minus I pi x divided by L. Okay, this is the first term. And then the second term would be e to the minus 4I omega naught t, and then e to the here I 2 pi x L minus E minus I 2 pi x L. Okay, so this step is correct. It's just a mathematical step. The problem is that whether we can interpret this as momentum eigenstate, right? Because we know that the momentum eigenstate in free space is actually e to the ikx, where k is h bar p divided by h bar, right? So let's see. This is the first consequence. If you kind of incorrectly use this as the eigenstate of the momentum in this potential well, then what will happen is that if you look at this is an eigenstate, this is another eigenstate, this is a third eigenstate, fourth eigenstate, and then if you look at the coefficient in front of all this eigenstate, although they are time dependent, but then we know that the probability, okay, of measuring the k, okay, the eigenstate k, is represented by the coefficient in the front and the amplitude square, right? So then if you look at them, these four, eigenstate of the momentum, then what you find is that the coefficient amplitude square is the same, right? They're all having 1 over divided by L, and then you also have a 2 here, and then this exponential minus I omega naught t, and then exponential minus 4i omega naught t in amplitude square, they all go to 1, right? So what you can tell is that if this is k1, the probability of k1, the momentum of the ground state equals to minus k1, right? Opposite direction equals to the probability of k2. Let's say k2 is the momentum of 2 pi divided by L, also equal to the minus k2. Opposite direction. So if we incorrectly interpret this as the eigenstate, then eigenstate of the momentum operator, then what you will find is that the momentum, the probability of measuring each momentum is the same, and it's not time dependent. Then you would draw the conclusion is that the momentum, when you're measuring the momentum, the expected momentum does not depend on time, right? Because then it would be 1/4, okay, h bar k1, the first momentum, minus h bar k2, minus h bar k1, this momentum, plus h bar k2 minus h bar k2. Right, so you always get a 0 result if you think this is the eigenstate. Okay, so so this is just one of the indication that tells you that, okay, in an infinite square potential well, this is not the eigenstate for your momentum operator. And then if you want to see a proof, you can actually go to page 25 on the lecture notes, and then they are actually prove to you that these two states, right, the eik1x and then eik2x, they two are not orthogonal to each other, and therefore they cannot be the proper eigenstate, okay, for the momentum operator. Any questions? So everyone understand that we can take this as momentum eigenstate, right? Okay. Now let's go into how to actually properly calculate this properly calculate this momentum expected value. So the way to do it is, again, use the definition, right? We know that if you want to calculate the expected value of an operator A, then what you do is that you do an integration, and then the state you try to calculate. While the state your system is in, conjugate your operator, act on the state, and then do an integration over the entire space. So we can just use this definition, or not definition, well, this is a derivation from the postulate. Then what we can do is that we can show P. Okay, P is integration from minus infinity to infinity, but then we know that beyond 0 to L, there's actually no, the wave function is always 0, so the integration can simplify to from 0 to L. And then we can have psi and momentum operator, and then psi dx. And then the momentum operator we've all learned before, h bar I partial x, right? It's the differential, first order differential. Okay, so this one, then what you do is you just plug in, okay, plug in the entire thing, and then let me erase this part so that we have enough space to write. Okay. So what you can do is that then you just plug in this to here, and then okay, there's conjugate, and also there's a coefficient, and then we can put the coefficient in the front, which would be 1 over L. And then there's also a coefficient from the momentum operator, which is h bar divided by I. So h bar divided by I. Okay. Okay, h bar divided by I. And then this side is the wave function itself, conjugate. So you're at first is sine pi x L e to the minus I omega naught t plus, right, because it's conjugate, plus sine 2 pi x L e to the I 4I omega naught t. Okay, just to save space, I will actually, do this integral in my mind, and then if you want to look at the complete process, you can turn to page 26 on the note. Okay, so there's the differential here, and then act on the wave function, and then a sine will become cosine, and then the coefficient pi over L will come to the front. Here is the same thing, but then it's 2 pi divided by L come to the front. So then overall you will have a pi here, you will have a L here, so L squared, and then this side would become cosine pi x over L e to the minus I omega naught t, and then this will be plus 2, okay, cosine 2 pi x over L e to the minus I 4 omega naught t, and then this integration, okay, this integration. And this is relatively straightforward. You have 4 different terms, okay, in combine. This multiplied with this multiplied with that, this with this with that, okay, and then it's also always sine times cosine, right? So you can actually use the triangle here is sine alpha cosine beta equals to sine alpha plus beta plus sine alpha minus beta divided by 2. Okay, divided by 2. So, so you can calculate all these 4 terms, and then I don't think it's a good idea to show the complete result here because the size of our board is very limited. So again, you can turn to page 26 in the lecture note, and then there's everything. And then I think the integration is simple enough. You guys should know how to do it. So I can, jump directly into the final result, which would be for h bar, okay, 3. Sorry, this is 8. 8. Right, and then you guys are probably curious how to get rid of the I. Okay, the I here will be get rid of by doing sine, because sine have the sine have an I here. So if you have 2 exponential, and then the minus, and then you will actually get an I there, and then you can return to sine, and then that make this back to a real number. Okay, so this one times e to the I 3 omega naught t minus e to the minus I 3 omega naught t divided by 2i. Okay. Yeah, this is h. Okay, and from here you can actually see that, okay, these two, the integration of these two is actually 0. And this term and this term, the integration is not 0, so that you get a e to the minus I 3 omega naught t term. Also this and that, okay, these two are also not 0. Okay, and you can convert this back to sine wave, right? So this is a h 3l, okay, and then sine 3 omega naught t. Okay, this is the expected momentum for this superposition state. And if you take a look at this, okay, this is actually looks pretty good, right? Because first, it's also time dependent, which means it actually agree with the previous result, which we say that the electron is doing a harmonic oscillation inside, right? So if you look at the momentum, okay, it's also doing a harmonic, okay, oscillation inside. And then the other thing is good is because in classical mechanics, right, we know that m times, okay, the mass times the speed is the definition of momentum, right? So here you see that if you do a derivative on position, expected position, you actually get from cosine minus cosine to positive sine, okay, which is this one. So there's a very high likelihood that in quantum mechanics, okay, this might be true. Okay, the definition of momentum at the expected value might be true. Okay, so let's see if we can verify that. Guess we can erase this part. One second. And then, so the thing that we need to see is whether the definition of momentum, okay, in the classical case, whether it's true for the expected value in the quantum mechanical case. Okay, so then the thing you need to do is just to calculate this, right? And then you can see that, okay, this part is time independent, it doesn't matter, so you take derivative of this one, minus become plus, so you have 3 coming out 16L omega naught, okay? And then 3 cancel with the 9 here, so it's 3 pi squared sine 3 omega naught t. Okay. Do they agree with each other? Any thought? Okay. So if you look at it, it looks like these two are different, right? It looks like it doesn't work. But then one thing that you kind of have to keep in mind is that the omega naught is the frequency, oscillation frequency of the ground state. And then it actually has expression here. Okay, it actually has an expression here. So what you can do is that you can plug in this omega naught back in here, and then you will see, okay, there's a pi square here, cancel with the pi square here. Let me just write it down. Pi square h bar 2 ml square sine 3 omega naught t. Right? Pi square will cancel each other, L cancel 1, then 2 cancel to the 8, right? So you actually get 8 h bar ml. Well, let's see. Oh yeah, there's an m here. Yep. M is right there. L, okay, and then sine, there's a 3 there, 3 omega naught t, okay. So you actually see that, okay, if you plug in this omega naught, you can actually show that the definition of, well, the mass times the expected velocity, okay, in the quantum mechanics case, actually equal to the expected momentum. Okay, so this equation is actually correct, at least in, okay, correct in our infinite potential well. And one thing I want to mention is that this equation is actually in generally correct for quantum mechanics. When you take the expected value of position and then you do a differential, and then you do the first derivative and then you time with mass, it actually will equal to the expected value of momentum. And later we'll actually talk about this more because this one is actually the Heisenberg equation, or the equation, or the quantum mechanics in Heisenberg picture. You will actually get this directly. You don't have to go through this trouble. Okay. So what it says is that if you're just measuring the expected position and then expected momentum, okay, the quantum mechanics case and then the classical case, they all follow this equation. Okay. Any questions at this point? Okay, so up to this point, we kind of have shown how to calculate the expected position, expected momentum for the eigenstate, and also for the superposition, of eigenstate, which can be, any states. So in principle, okay, if you see any question about, what would be the measurement result for the infinite potential, well, you should be able to know the answer. The only thing that we have left out is that some of you actually asked this before, is the initial condition, right? Let's say if you want to know the dynamics of the electron inside the if you want to know the dynamics of the electron inside here, for example, if I put one electron here in the center as a delta function, and then I want to know how the wave equation evolve with time, right? So what I briefly mentioned this before is that as long as you can get the eigenstate of the system, which we could, okay, in this case we already get the eigenstate, then what you can do is that you can write down your wave equation as a superposition, okay, of all the eigenfunction with the coefficient like this, okay, with the coefficient like this. And then if this is actually the eigenstate of the system, this coefficient will be time independent. Okay, so it's just a number here. Then you can imagine, okay, why then why there will be dynamics here is because although this number is just a number, time independent number, but all of your eigenstate have a time evolution term here, so that all this state will actually do interference, just like in our superposition state between the ground state and the excited state. Although, okay, this coefficient is 1 over square root of 2, okay, but then the electron will actually move back and forth in the potential well, okay. And for system, okay, to actually know all this number, one thing you can do is that you can use the initial condition. And then for the initial condition, usually what people give you is that you have a wave function at t equals 0, and this wave function is known. Okay, and this is something you might wonder, okay, how is that possible, right? Because it's from an experimental point of view, right? It's impossible to actually measure the entire waveform, because whenever you do a measurement, you collapse, you only see a probability wave, right? So the way that people do this in real experiment, for example, is that if you want to release the electron at the center, then what you can do is that you just measure the position of the electron at the center. Okay, whenever your detector shines, that means, okay, there's an electron here. Then you turn off the detector, then the electron will start from the initial place, right? Because we know that after measurement, if you measure A, and then you get the eigenvalue AN, it's your measurement result, then your state will become the eigenstate corresponding to this eigenvalue, right? Because that's the only way that you can ensure that if you do the second measurement immediately after that, you will get the same result, okay? So if you want to start the electron here, just put the detector here. And then when you detect it, you turn off the detector so it will not do the second detection. Then you set this quantum system to this initial state. The other way to do this is that you can measure the energy. Okay, energy is also something you can measure. Just do a measurement, and then when the measurement corresponds to, well, the measurement of course is a certain eigenvalue, then the state becomes the eigenstate. Okay, and that's a way, actually, in general, that's a way to prepare a quantum state. Okay, and later in quantum computing, actually, if you read any quantum computing book, there's a condition for a usable quantum computer is that you have to be able to prepare the initial state. Okay, this is actually in general a difficult problem. Okay, it's not just like in classical mechanics you can just for example, in your violin string, or guitar string, you can just give it a waveform and then let go. It's not like that in quantum mechanics. Okay, so in general, then suppose, okay, because we're just in a class, we're not really building a quantum computer. Okay, suppose I give you the waveform f of x as your initial condition, then what can you do? How can you get this coefficient alpha n? So the way to do this is that write this down at time 0. At time 0, this equation is also correct. So you have psi x time equals 0 equals f of x equals to this sum okay, and then in this case, and actually in most of the situation, at time equals 0, this time evolution term is just 1, right? Exponential of something 0 is 1, so that this return to the time independent eigenstate. Okay, so it's just the sine function here without the time evolution term. Okay, let's write it down here. Psi n x equal to okay. Then the next step is just to do integration on both parts. Okay, and the way this works is that we know that all these eigenstate, they are orthogonal to each other, so that what you can do is that you can have integration of 0 to L, and then you have f of x, and then you times the mth state conjugate, mth eigenstate conjugate, and then do the integration. And then on the right hand side, it's the same thing, right? Alpha n, and then you do this integration. The reason I moved the integration inside is because in general you can switch the order between sum and then integration. And you have alpha psi n of x times psi m of x dx. Okay, so this equation is the same as the upper equation, but what you do is you multiply the conjugate of a certain eigenfunction, and then you do an integration. Okay, and then here, because we know this is the integration here is a delta function equal to 1 when n equal m, 0 when n not equal to m. Right? So this sum of n, okay, only have one non-zero components when n equal to m. Right? So the right hand side simplify to alpha m. Okay? So this is how you get the coefficient alpha m, just by applying the eigenstate of m conjugate and then do this integration, and then you will get it. And for this special case, you will actually see that this is just a Fourier transform, because if you actually really plug in the eigenstate, you will see that it's square root 2L, a function, and then sine m pi x divided by L dx. Okay, so this is just a discrete Fourier transform. Okay, discrete Fourier transform. And so this is very interesting now. I don't know if this is taught in EC mathematics class, but then if you look at this, okay, in general, what it tells you is that, you know, any function, fx is actually can be any function as long as it's valid, it's smooth, can be efficiently expressed by a Fourier series that is constructed by sine, right? Sine pi x, sine x, sine 2x, sine 3x. And this sine wave is actually derived by this infinite square well. So let's say if we change a different system, right? Let's say if we have a harmonic, well, if we have a harmonic oscillator where the potential energy is kx squared, okay, then apparently you will get different eigenstate, right? The mathematical form of your eigenstate will be different. But then you can also express the same wave function f of x, right, with those eigenstate, right? So in general, your f of x can be expressed by another set of eigenfunctions. Okay, so that tells you, what that tells you is that Fourier transform is not unique. It's not the only transform you could have mathematically. Okay, probably some of you know Laplace transform. And then there's other type of transform. And you know, this, I shouldn't say this, but if some of you are learning machine learning, they do this all the time. Okay, you do Fourier transform, you get from time to frequency domain, and then you see some signal that is not visible in time domain. If you change a different transform, okay, by using a different eigenset, then you can transfer from time to another space. Okay, and then you will see other signals that you wouldn't be able to see in time domain. And then if you mix a few of them and then you make the data set large enough, then you have something called machine learning. And when I first learned this 2 years ago, I was kind of thinking, is this a joke or something? Because you know, physicists are very familiar with this 100 years ago. Anyway, I shouldn't trash talk another area. So they're actually very nice, and then you can find job easily in that area. And then in general, they're useful. And if you're wondering how intelligent they are, there are numerous videos on YouTube, and then you'll be surprised like how they actually work. I still find machine learning very fascinating and then confusing at the same time. Okay. Any questions? Okay, so the next part is a little bit, well, we only have 6 of you here, but then the next part is directly related to midterm. And it's, well, it's fair because we have recorded video, so it's not like they missed the class. Okay, so the next step is actually, for this potential well, is actually to make it into a real-world potential well, because in real world you don't have infinite potential well, right? This is just not physical. Okay, so in general, the potential well will look like this. Okay, this is x, and then you have on this side you have V1, on this side you have V2. In if you're really fabricating a device, usually V1 doesn't equal to V2. Okay, and just for most of the time the you just don't get that symmetric system. Okay, so this is general case. If you can solve it, then you can get, in principle, you get all the solution for potential well. But then you can further argue that in real world you can have a sharp change in your potential energy, right? So people would further go, okay, then this is probably there's a curve here, right? It's not really that sharp. There's a curve there. Okay, and believe it or not, this is very difficult to solve. Okay, and then there's actually there is analytical solution, but then to actually get the ground state and then the eigenstates, energy of the eigenstate, you actually need to use numerical calculation. For example, use MATLAB or Mathematica to get the numerical value. So in this class, for the sake of saving our time and then without losing any physics or without losing any mathematical tricks, we'll just do half of this. Okay, the state, while the potential well we're going to use is a half infinite potential well. Okay, so on the left hand side, on the left side, this V1 goes to infinity. So left side is still a hard wall. On the right side, you have V2, that's a finite number, and then again the well width is L. Okay, and then this actually will work pretty well because what you have is that, okay, you get yourself another boundary condition here, a good boundary condition here. And the second thing is that whatever happened here between this, at the boundary of this V2, okay, whatever happened here, you can kind of think that it will happen the same way in this V1 well, okay, if V1 is finite. So that solving this wouldn't lose any physics insight for the system, okay. Now, so let's erase this. Okay, so the way that you can write down the Schrodinger equation, well, you have to write down Schrodinger equation again. And then in this case, we're only interested in the eigenstates. Because beyond once you solve the eigenstate, then it's the same story, right? You use the eigenstate, you use superposition, and then you calculate those things. So it's the same thing. So we're only interested in the eigenstate, so that you only need to solve the time-independent Schrodinger equation. Okay, if you're only interested in the eigenstate, then you only need to solve time-independent Schrodinger equation, and then the H, the Hamiltonian, is again the kinetic energy plus momentum. Kinetic energy plus potential energy, and then your potential energy this time is infinity at x smaller than 0, 0 from x between 0 to L. And then V1 from when x is larger than L. Okay. So the way that to solve this Schrodinger equation is actually quite representative. The way you do this is that if you look at this, okay, there are actually two very different regimes because the V is different there. So what you do is that you first solve the Schrodinger equation inside this range, and then you solve the Schrodinger equation in that range. Okay, so you actually give yourself two Schrodinger equation. So So from x larger than 0, smaller than L, okay, you plug in the v into here, v is 0, so what you get is that 2n okay, so this is the first equation you can solve. And then the second equation is this one, right? Here I actually, in the note, I use v knob. Okay, v naught. Then when x larger than L, what you can get is plus v knob equal to En. And these two equations is actually, if you really look at it, they're actually the same, right? You can move this term to the right, right? It's just a number times the wave function equal to a number times the wave function. So you move this to the right, then what you get is that you get En minus v knob times your wave function. Right, so these two equations are the same, it's just the number is different. Okay, number is different. So now think about it. Okay, if En, we know that En is the energy, eigenenergy, or the energy of the eigenstate, then does it actually mean something if En is larger than V naught? Right, think about it. If your electron has more energy than V naught, in the classical case, what will happen? Right, if it's in a well and then you have kinetic energy larger than this, then what it would do is actually go out of the well, right? So you can kind of see that if En larger than V naught, then it will be, okay, the electron will escape. And then, how do you kind of see? Well, let me put it this: mathematically, how do you know if this is correct, right? If you solve this equation and then you find out that the wave equation at x go to infinity is not 0, then you know the electron escape, right? Means that your electron has some probability of appearing at the position of infinity, right? Then you know that the electron escape. And then also from the classical point of view, okay, if the energy is smaller than V naught, then electron should be confined, right? Should be confined. And then the way to test this again is to see at infinity if the wave function goes to 0, right? If it goes to 0, then the probability of the electron showing up at infinity is 0. Okay, so it's not escaping the potential well. Okay, so with that in mind, okay, we can first solve the first one. This is fairly straightforward. It's the same sine wave you have because you also have the boundary condition here. Okay, you can solve cosine and sine, but then cosine doesn't satisfy the boundary condition. So you have psi n x equal to equal to a coefficient. Let's see what coefficient I use. Okay, I use a coefficient sine, okay, square root of 2m en divided by h bar square, okay, x. Okay, so this is the solution for the first equation with boundary condition psi n x equals 0 equals 0. Right? If you use this boundary condition, you can actually get this. Now, for the second equation, let's see if we have En larger than V naught. Okay, if the energy of your eigenstate is larger than the potential energy, then this term is positive. Right? This is positive. So we already know En here is positive. So that these two will get the same equation, same solution, just replace En with En minus V naught. Right? But then here you don't have boundary condition. Right? So then the solution will be psi n x. Because you don't have a boundary condition, then you can have both sine and cosine. Okay, sine 2m En minus V naught h bar square x plus, let's give a number here. Let's use alpha 1, alpha 2, cosine 2m En minus V naught h bar square x. Okay, so on this side, outside the potential well, you will have this solution if En is larger than V naught. Okay, if En is larger than V naught, and you have both sine and cosine because now on this side you actually don't have a boundary condition to use. Okay, and if you look at this, you will see that it actually satisfies the electron escape condition, right? Because sine and cosine, they just oscillate with the propagation of position. It doesn't decay to 0, right? So this, when you solve this, you know that the electron escape, or we say electron can escape, right? And usually people are not interested in this one because, you know, if electron escape, then it's just an empty potential well, right? There's nothing in it. So usually we don't consider this. Okay. But then, of course, it's interesting to know the escape energy, right? How much energy you need to energize the electron for it to escape, and then usually you should operate. If you want to move the electron away, then you operate at that energy level, higher than that energy level. If you want to just confine the electron, then you avoid that energy level. Okay. Now let's go down to the other case, En smaller than V naught. Okay. In principle, you can just use this solution. It's the same thing. I mean, like if you plug it in, and then you will see that this, regardless of En larger or smaller than V naught, this is actually a valid solution. But then the problem is that, okay, if this is smaller than 0, then you have a square root of something smaller than 0, then you get imaginary number. Then if you have imaginary number, then your sign of imaginary number, you have to calculate that. Okay, and the way to do that is actually I can show you how we can get this done. Okay, if you have sine and then imaginary number, let's say ikx inside, then what you can do is that you use the you expand the sign in terms of e to the ix minus e to the minus ix. Okay, you do the exponential thing, and then e to the I. Now there's an I here, so ikx, iikx, right, minus e to the I minus ikx. Right, so I give you minus 1, so you get e to the minus kx minus e plus kx divided by 2I. Okay, so you can kind of see that you can use the same solution. As long as you're clear in the math, you can actually get the correct result. Okay, this is exponential decay and exponential growth. Okay, and then we'll see that it's the same thing here. If this is smaller than 0, then you have minus I on both sides. That means if you do a differential twice, you should not change the sign of your function. So the best way to do that is exponential. Okay, exponential something. Right? If you do twice the derivative, it gives you k squared. Okay, if k is a real value, real number, it doesn't have to be positive or negative, just a real number, then you know that the sign will not change. Okay, so you can solve it either way by using this and using some math, or just directly solve that. And what you will get is what you will get is psi n x c equal to c e to the minus square 2m Okay, so the h bar square is inside the square root, and then x is outside the square root. Okay, just to make that clear. Plus d, because you have two solutions, your k have a k squared here, could be both positive and negative. So this is a negative one, and then you have a positive one, and then because we know that you can be in superposition of them, right? So e to the plus 2m Okay, and then now we to make things simpler, we know that this solution, this mathematical solution is not physical, because the wave function will explode to infinity at position infinity. That's against confining the electron, right? That means your electron is always at infinity. That doesn't make any sense. So for confined electron, you can always use this as a boundary condition, right? Your wave function at position goes to infinity has to be 0. That means your electron is confined. Your electron will not go to infinity. So with that boundary condition, you can get rid of this term. Okay, you can get rid of this term, so that your wave function, you write this down, c exponential Okay, so this is the solution here. Within the potential well, it's a sine wave as usual. There's a coefficient here we don't know yet. Okay, and outside the potential well, it's an exponential decay. And then there's a coefficient in the front. Again, we don't know yet. And then in this solution, you also have the energy En, which we don't know yet. Right, so there are 3 coefficients we don't know, so you need 3 equations to solve them, right? And one equation is fairly straightforward. It's the normalization condition, right? Your normalization of your wave function amplitude square has to be 1, right? That's the probability of finding the electron in the entire space is 1, right? So that would give you one confinement. That's okay. First, any questions regarding these two solutions? Okay. Then let's put it down here. You have 3 unknown, A, C, and En. Okay, so you need 3 equations. And then the first equation is just the normalization condition. Okay, this will give you a relationship between A, C, and E, and then of course it's a relatively complicated equation. Okay, and what could be the other 2 equations? I mean, we already solved Schrodinger equation. There's no more for us. So the next 2 equations is actually very interesting. Let me write down the Schrodinger equation first. Time-independent Schrodinger equation. Let me ask this. So for the Schrodinger equation determining the entire system, right? And does that require our wave function to be continuous? The way I can ask this is that, can you have a wave function? Let's say the wave function is real, just for simplicity. Can I have a wave function that is suddenly jump? Can we have that?
I guess not, because it would not be differentiable at that specific point.
Yeah, great. So at this point, right, then the differential of your function will go to infinity, right? Will go to infinity. And then also the same, and what that means is that, because look at here, you have a second differential term here, right? If your first differential is already infinity, then actually the second differential is not well defined. There's no definition for that. Okay, or you can simply think, okay, this is already infinity, then this one is also infinity. Then you see, okay, then this term is not infinity. The wave function doesn't go to infinity unless it's a delta function. Vx is not infinity unless it's a delta function again. And all these are not infinity, right? So you cannot balance this equation if one of the term goes to infinity, right? So what that tells us is that this cannot go to infinity, okay? This cannot go to infinity, and that means this has to be differentiable. Actually, I never learned that word in English. Okay, I guess you guys understand this. And what that dictates is that, okay, this function itself also has to be continuous, right? The first differential of the wave function also has to be continuous, because if you plot that out, okay, if suddenly you jump, then the second derivative would go to infinity, and then your Schrodinger equation would not be satisfied. Okay. So what that tells us is that at any given point per psi n x, we can say at x equal to a position minus is at the left side of a point. Okay, left side of a point. The value has to equal to the function, and then at the right side of the point, we put a plus there. Okay, so it's infinitely. So this point is it's infinitely approaching this point from the left. Okay, this is infinitely approaching this point from the right. Okay, and then the same apply to the first derivative of the wave function. So it's the continuity of the of your Schrodinger, well, of your wave function. Okay, so this gives you the additional two equations. Okay, it's hidden in the Schrodinger equation, and then you just have to, just have to look for that. Okay, and then this will be very, very straightforward now in terms of the solving this wave function. Is that okay? At the boundary of the potential well, right? On the left side, on the left-hand side, you have a sine wave. On the right-hand side, you have exponential decay, right? And the value, absolute value of these two has to match at x equal L. Also, their differential has to match at x equal L. Okay, that gives you two equations, and then we can quickly write down here, and then we have 4 minutes left. So this will give you two more equations. The first one is a sine square root 2m e n h bar square at x equal L will equal to the second one, c exponential minus 2m v naught minus e n h bar square L. Okay, so this is the first, well, second equation. The first is normalization equation. And then the third one is the differential is the same, then you quickly do the differential here. You do derivative of sine, then the coefficient come out, and then you become cosine. L, okay, equal to exponential, you do differential, then the coefficient come out, minus c, okay, 2m. And then exponential minus at x equal to L. Okay, then you have these three equations now, and then you solve it, and it's done. Okay, and there's, to my knowledge, there's actually no analytical solution. Okay, but then we will try to solve it in the next class, and you would see some see some insight from this. And then the other thing is let's plot out, okay, what this waveform actually look like, right? So let's use, for example, the ground state. The ground state will look like something like this. Okay, we already say for any ground state you should only have one maximum, right? You should only have one maximum, so it will look like this. And then when you approach here, then it's exponential decay. Okay, but then the decay has to match the curvature here, so that it's a smooth transition, so that you satisfy the continuous condition. And then this will be the shape of your ground state. Okay, and then you can try to plot the first excited state, second excited state, and then using the principle that, okay, there will be some exponential decay here, and then inside here is a sine wave, and then you can actually draw all of them. Okay, that's all for today. I will stay here for a few more minutes.